Good day. This is our presentation on the work that we have done with our smart avocados, specifically looking at optimization of packhouses by collecting data on what happens to an avocado as it travels through a packhouse specifically. The presentation will be done by myself, Wynand Steyn, as well as Andre Broekman. Both of us have been involved in the project from the start, so please listen to the details, and if there's questions in the end, you are welcome to bring them. So in terms of the overview, what we will cover, we will give you some of the introduction on objectives just to understand the background. Then talk a bit about the SMAVO or the Smart Avocado instrumentation itself. Look a bit about the field testing, about what we have done, and then very obviously from that the data in the field testing, the results, the statistics, what did we learn from this, and then draw some conclusions, and in the end there's an opportunity for questions and discussion. So what is the question that we want to overall answer? You harvest agricultural products, avocados in this case, and you start a transportation process from the field all the way through to the market. And this goes through a process and packaging part, some local transportation networks, maybe some transcontinental transportation, and then in the end it has to get to the market and to the consumer. So in this bigger picture, it's important to look at the quality of your local as well as your larger transportation networks. So the specific objectives that we had for this project was to quantify the potential damage of avocados in a packhouse environment specifically. So looking at how can we optimize our sensors, and then develop some kind of descriptive metrics and statistics so that one can start to compare different packhouses and processes with each other. And very specifically to make sure that we've got some data-driven recommendations and guidelines and not just perceptions that guide us in this process. So the SMAVO instrumentation is based on some developments that we've done at the University of Pretoria over a number of years, where we looked at the development of standalone sensors. And this developed into our first 3 SMAVO prototype units that we used in some field testing since March 2019. And evaluated them, and then realized that we needed some updates to make sure that they are moisture proof and a few of the robustness issues to sort that out. That gave us a slightly different layout, and you can see a watertight smaller enclosure that we developed that goes into the exoskeleton, and on the inside of this smaller enclosure we've got the sensors, we've got the battery, we've got a reed switch to make the switching on and off and things like that much better. So this was our optimized version of the SMAVO. In terms of this optimized SMAVO, smaller density means that it can float in water, similar to avocado. It's food grade filament, so it should not affect any of the processes. And the primary sensors that we were interested in terms of our data were the 3-axis accelerometer and the 3-axis gyroscope, both of them collecting data at 100 Hz. So a lot of these details are described in some publications. The article link is available. If you search for the article itself, you can get all of the details of that. We are not going to go into the presentation in all of those details today. In terms of the field testing, obviously it's quite a large operation and a lot of logistics and planning that needs to go into this, especially because most of this was done during COVID-19 lockdown. So we had 2 highly trained and experienced technicians that assisted with the field trials. They ran through the field trials and they planned the whole process, and they had a fixed process of how to handle the instrumentation, how to make sure that we obtain similar data from each of the packhouses and process this to ensure that we don't lose any of the data. In terms of the packhouses itself, we in the end visited 20 packhouses. There was a possible 37 packhouses, but due to various sort of harvesting issues and COVID lockdown and so on, we managed to do 20 of them over a 7-month period. They did have a good geographic spread, some of them in Limpopo, KwaZulu-Natal and Mpumalanga, and also using bins and crates to bring the avocados into the packhouse. So during this process, we saw a number of different types of mechanization and pack lines. So we think through the process, we got a pretty good idea of what happens in the typical packhouses for avocados in the country. In the end, for these 20 packhouses, we made sure that in the analysis and so on, we anonymize the data. Obviously, at the background, we've got a secure place where we know exactly which data comes from which packhouse, but for all the analyses and all the reporting and so on, we kept it anonymous so that we also keep any possible bias out of the analysis.
Thank you, Prof. Steyn. So an important disclaimer when we talk about the results from the study is to realize that we're doing a relative comparison. A packhouse is not in and of itself a bad or a good packhouse. We tend to refer to them as optimized, an average packhouse, or an unoptimized packhouse, which can use some improvement based on the spread of data which we collected. Typical data processing pipeline that we used, we store all the data from the SMAVO as it goes through the packhouse on the SD memory card for permanent storage. We subdivide this data into a fixed folder structure. We automatically process all of this data into usable information using the Python environment, and we aggregate the representative statistics into a central spreadsheet or database and run our analysis from there. In total, we had 134 complete and viable SMAVO runs, which recorded complete data, more than 2,500 files and 12.7 million acceleration data points. And as Prof. Steyn mentioned, we randomized each packhouse with a unique identifier to ensure anonymity. We calculated 6 key descriptors which we considered important for the analysis. The approximated runtime, how long the SMAVO takes to travel through the packhouse, the number of rotations, how many times it falls or is in free fall, and the duration thereof, peak-to-peak acceleration data, and cumulative kinetic energy. Based on these descriptions, we developed a relative classification score, and from that we work with the packhouse processing quadrant and the damage index score. So this is the main score which we say is a packhouse classified or optimized or unoptimized. Typical results for runtime, on average it's 7.7 minutes with a standard deviation of 3 minutes. On average, the SMAVOs will rotate 81 times with a standard deviation of 49 rotations. 29 free fall events on average per SMAVO, so quite a number, with the mean fall distance only 28 millimeters. The maximum free fall distance, or the average of all the samples thereof, was 112 millimeters, and the total cumulative free fall distance approximately 800 millimeters for a given SMAVO. Peak-to-peak acceleration data, so 50th and 75th percentiles, is about 1.6 to 1.8 Gs. On the more extreme end of the scale, the 99th and 100th percentile peaked at 6.5 G and 10.5 G, so very significant impact events were recorded. The cumulative kinetic energy, how much energy had to be absorbed by the SMAVOs, the average and the standard deviation with both 129 joules, so quite a large spread, with certain packhouses exhibiting a very large maximum of over 1000 joules, which is 600% more than the average. So what do we do with all these statistics? We want to classify a packhouse based on this quantitative data into optimized, average, or unoptimized packhouse. And we can look into detail where do these impact events occur over the surface of the SMAVO, and how can we link this with the post-harvest stresses. What makes a optimized packhouse, or what elements should be removed from an unoptimized packhouse to make it better. So, based on the consultation with the packhouse managers, literature study and academic researchers, we selected the cumulative kinetic energy and the total free fall distance to develop what we call the packhouse processing quadrant. This is our main tool for classifying these packhouses, and this is what it looks like. On the x-axis we have the total free fall distance in the logarithmic unit, and also on the y-axis the cumulative kinetic energy, also the logarithmic unit. In short, you don't want an avo to fall, and you don't want it to absorb a lot of energy. So you want your packhouse measurements to be on the bottom left hand corner. If the smather falls quite a bit and it's handled roughly, so lots of impact events, then your packhouse will sit in the top right. And the delineation between these different quadrants is determined by the average of those measurements. So again, it's a relative distribution of packhouses. And then if there's excessive dropping, bottom right hand corner, we give it a score of 3. Excessive handling, top left corner, DSI or damage score index of 2. So this is the classification thereof. So what do we see? There's quite a large spread for the different packhouses. On average, bins have a slightly better score than the crates, and the mean DSI is 2.13. If we compare all of these statistics together, we then sampled a packhouse which we considered optimized, average, and unoptimized based on all of this data to look into more detail what's going on. If we just consider regional differences, the average DIS score was for KwaZulu-Natal 1.5, so first place, Limpopo slightly worse 2.2, and then Mpumalanga 2.6 in third place. This also corresponds with the observations of the technicians, whom reported that KZN looked for them to be the most optimized packhouses. Overall, we see that the bins show improved peak-to-peak acceleration data, but it depends on what kind of statistic that you look like. Only minor differences, but this appears to be a function of the packhouse size and the mechanization level itself. So you cannot necessarily say bins or crates or one is better than the other. You have to look at the whole picture holistically. If we then consider the force distribution on the surface of the smather for an optimized packhouse, we typically see that it aligns with a section to the smallest second moment of area. You'll see a picture shortly of what that looks like. And then the unoptimized packhouse, because it's handled more roughly, it has a much more uniform distribution of damage around that smather. So typically the large flat faces tend to align with the rollers, both with the avocados and the smather, and this then corresponds to that distribution that we see about one single axis, similar to the bottom left hand figure over there. The acceleration history for an optimized packhouse, we have a relatively short duration and a small acceleration amplitude. Compare this to the unoptimized packhouse, where we have a very large acceleration amplitude and a very long duration. We do not want to handle these avocados for a very long period of time and with a minimal amount of force. So the distinction between these two packhouses are clear. There's a significant variation in the acceleration history if we consider just the samples within a specific packhouse alone. So even just one packhouse, there is a significant amount of variation, contrary to what we expected. Some interesting events: we had one smather that for 7 minutes floated in one of the water baths, which seems like a very long period of time. And then also when the avocados are dropped into the water from a bin or crate, we see extremely large and high impact acceleration events once it enters the water, when it hits the water a second time after it bounces out, and then interaction with its neighboring avocados as well. The number of rotations, these also corresponded with the average damage index score, and the freefall history, it's not always correlated between one or another, but for an unoptimized packhouse, there tends to be many more freefall events associated with the smather. We also observed events where there were poor handling of avocados. Of course, we can resolve this with improved training, not to drop the avocados from a significant height. Different loading methods. The preferred method which we found from the data is the dip method, as we classified over here, bottom right hand corner, where we gently lower the avocados into the water bath, compared to the other two methods where it's more rough handling of your avocados. One of the major events that we saw that had the most significant impact on the damage index, and of course then the post-harvest stress, was the rollers. It's extremely detrimental to the acceleration that we measure from the smathers, and smaller diameter rollers tend to reduce the acceleration amplitude, and then if we add more avocados, they tend to move through the whole process a lot quicker. Otherwise, they tend to stagnate and idle on the rollers, and this just accumulates the damage more and more. So this is an example of different rollers. You'll see for the optimized packhouse, we have a short duration and smaller amplitude, compared to an unoptimized packhouse with larger amplitudes and longer duration, where these avocados are present within the rollers. This is just some images of the most optimized packouts which we identified. There's a greater level of mechanization and more consistent handling, smaller drop heights, and individual conveyors where the avocados are handled in a generally more acceptable way, which we could just discern visually. But this was characteristic of an optimized packhouse. Finally, once we have all this data, can we develop some sort of a model? Linear approximations don't work that well, only about 55% accurate. We looked at correlation matrices and the interaction between the variables. And in the end, we developed a very simplified neural network with 3 fully connected layers, very few trainable parameters, and we could boost this classification to 82% accuracy. All this means is that you have 9 key statistics that you put into the model, and out comes a classification of that packhouse with an 82% accuracy score.
Thank you, Andre. So if we look at some conclusions based on what we've done, we are pretty happy that the optimized version of the SMAVO worked well. We obtained the type of data that we were looking at, providing us with insights that I don't think we had previously around the whole packhouse dynamics. We could see some regional differences, we could see differences due to levels of mechanization, and quite importantly, it was possible to develop a classification system that's based on collected data, and one can discuss exactly where the cutoffs are and so on, but at least one has got data available to base this whole discussion on. We could show where there are some of the negative impacts around things like the fast roller speeds and stagnation and so on. And this also provided us in the end with the neural network model that can assist in a more automated classification process in future. In terms of what do we now think, what is the future technology development around this? The SMAVOs successfully provided us with this first large-scale representative quantitative evaluation. But now there's various things that can be added to this. There's things like LoRaWAN sensors that uses a wireless type of environment to provide information from the sensors continuously so that one can have a continuous evaluation of your system. Some of the edge intelligent analysis provide for the basic analysis to be done on board, which makes a lot of the calculations and processes after the data collection much quicker. Then also what we think as some of the future research endeavors is to really look at now the complete quantification from farm to fork, really from the plant to the consumer, that you've got a complete transportation network based on the type of analysis and energy that the avocados will experience during this process. It provides us with online type of data aggregations that should be part of such a future endeavor. Also, if you look at it wider, you can start to get to a digital twin environment of transportation of fresh produce, where you can really start to model this in much more detail, further it to not only local transportation but also international transportation, looking at what happens to avocado during normal shipping operations, for instance, and then also look at, with the high security around avocados and theft and issues around that, how one can possibly make use of blockchain technology in terms of this whole post-harvest certification of where does the avocado comes from that I buy at the market. Based on all of this, we would like to acknowledge a lot of support that we obtained. SAAGA, obviously, for the research funding and making the links to industry available. Then all of the farmers and managers and all the persons who really assisted us quite a lot in terms of the packhouse data collection. Sarel Kutzer and Dave Ventura, they were our 2 on-site technicians that made all of the data collection possible. Without all of that data, all of that is just a bit of theory. And with all of that, you are welcome to ask questions, and let's take the discussion from here. Thank you very much.